Okay, welcome back, everybody. So, this is now introduce Markus Land. What's up here? Markus is going to talk about manifolds, algebraic theory, and excision.
Right. Yeah. Thank you so much. Thanks for being here. Thanks for having me. I was sneaky and prepared something, but it's only sort of to reassure people. It's not relevant for the talk, so don't worry. Okay, so as Natalie said, I want to talk about manifolds, K-theory, and excision. So this was, the title was done on purpose. So K-theory is in the middle. That's going to be, in some sense, the central topic. Excision is going to be a method of calculating K-theory in particular instances, which I will come to at the very end of the talk. Manifolds, in the context of this talk, arise as one possible motivation of how algebraic K-theory arises in an area which is more of a geometric flavor. It's more of a topological flavor in the sense of Natalie's talk, in the sense that it's about the global structure of manifolds, but nevertheless. Okay, so what I want to roughly say is that algebraic K-theory is something that associates to a ring, a sequence of groups over the integers, appearing groups called the K-groups. And in principle, this collection of invariants of the ring is sort of the study of those, something we would call K-theory. And it's sort of built from the study of projective modules over a ring and their isomorphisms. Or maybe if you insert a bit more general things, a scheme, say vector bundles over a scheme and their isomorphisms. So this is roughly what K-theory does. And I claim to motivate a bit that it's not something that's very particular to just rings and projective modules. I want to motivate briefly that it does affect different areas of mathematics and somehow relates them in an interesting manner. So for instance, in the number theory case, the kind of rings that you would extract into maybe global or local fields. Fields would be interesting things you can try to calculate all the rings of integers. And so I'm not an expert in number theory, but I also want to take this talk to advertise, among the other people working here, that Justin is now newly in Copenhagen, and he's very well aware of relations K-theory and number theory. So if you're ever interested, let me know, and then we can go to Dustin together and learn more things. Okay, so as I said, K-theory is about vector bundles on schemes, or say finitely generated projective modules over a ring. So it's sort of obvious from the definition that it relates to algebraic geometry, because well, it's about vector bundles over schemes. But there's also more intricate relations. It has, K-theory relates to Chow groups, to cycles, to motivic homology. So there is a very deep and interesting relation between K-theory and geometry. On the geometric topology side, it's not so obvious somehow how finitely generated projectives would tell you something about manifolds, and that is why I want to take some time today to explain some of the old ideas of Waldhausen and Hatcher that sort of relate these two areas. But I do want to say right from the beginning that the kind of rings that one would insert here is group rings or fundamental groups of manifolds, say. So highly typically non-commutative rings, maybe not the typical thing you would encounter in a commutative algebra course. And then there is a variant of this, which I will get into later, which is sort of inserting a more topological flavor, where instead of taking from a manifold its fundamental group, you take all of its loop space, the base loop space. This is a group in spaces. You can concatenate loops. Informally, you can think this is just still a group in spaces. And instead of taking a group ring over the integers, which is sort of the initial ring in just ordinary algebra, you can take a group ring over the sphere spectrum, which is in some sense in the higher algebra the initial ring. It's in some homotopy theoretic analog of a group ring. And that is sort of the one that will relate the topology of manifolds to K-theory. Sort of. It's not the discrete thing. And we'll take some time to explain roughly why it is that this happens. And then there will be an instance, there's a comparison map from this sort of very topological ring to this ordinary group ring. And this map has an interesting behavior on algebraic K-theory. And that's a very general and important property of algebraic K-theory, and we'll come to that and exploit this in the context of excision at the end of the talk. So roughly, this is what I'm trying to say. If you cannot follow, please stop me. No, there's one more thing I want to say. So what are prototypical type of things that arise, and just something I find fascinating. So for instance, on the one hand side, there's a theorem that says that if you look at the homotopy groups of diffeomorphism groups right boundary of the odd-dimensional disks, you rationalize those groups. And then there's a theorem that says those are isomorphic to the algebraic K groups of the image transgression class. I don't know if that's sort of surprising if you have never seen something like this. And this is, okay, I have to be careful. So this is roughly for 2n, roughly in range, where 2n is, where the stars or the index is less or equal to 2n third, so roughly a third of the dimension, due to Faraday and Chiang in the end of the 70s. And has recently been upgraded by a recent PhD student from here, so Manuel Land, proved this for star less equal to n minus 5. And I think this year, last year, so very recent. And Oscar is going to tell us about homotopy groups, rational homotopy groups of diffeomorphisms of even dimensional disks, but with a very different method that I'm going to indicate today, which is sort of a more modern, a different approach. Nevertheless, this approach is the approach I'm trying to indicate today is also sort of applicable to more things than disks. Okay, so that's something where just the K theory of the integers, and I should also say that these groups are unknown, it's not so complicated, sort of relate to diffeomorphisms of disks. On the other hand, there's another thing about the K theory of the integers that relates to number theory. So here we have a conjecture called Kumar-Diver, and it says the following. So again, I'm not a number theorist, but the question is, does P divide the class number or does it not divide the class number? Or you take the P supernomic extension of Q, its maximum real subfield, and ask whether or not P divides this. I think the conjecture is that it does not divide this. I don't know. That this statement is equivalent to the vanishing of the 4K dimension. Okay, so both a statement about homotopy groups of diffeomorphisms of disks and about class numbers of these cyclotomic extensions or the maximum real subfields relate to algebraic K. Personally, I find this fascinating. We don't have to follow this, but nevertheless. Okay, so the rest of the talk, I want to say something about geometric topology and then about a particular way of trying to calculate K theory. And I want to start real slow, such that if you get bored because you know things, or you get lost because you're not so into what I'm saying, there's still going to be a little exercise that you can try to solve along the way. So here's a very basic question I want to ask. So how do we show, in general, how can you show that two manifolds n, say n0 and n1 are diffeomorphic? That's a reasonable question. I mean, at least we pretend in the beginning when we talk about manifolds, we want to classify them. Ideally, you want to have a list of, those are all the manifolds. Now, suppose you write two down, and they are diffeomorphic. I mean, if they're not diffeomorphic, typically you have tools to say, well, there's some invariant that distinguishes them often. So, but if all this fails and you start to think maybe they are diffeomorphic, at the end of the day, you probably have to write down the diffeomorphism. So, one instance where this works well is this sort of exercise examples. Where you can look at S1, just a set of complex numbers with modulus 1. And you can take the real numbers and divide out the action of the integers. Those are not the same, but they're diffeomorphic. And I think you can try to work with them. So a bit more complicated, but still along very similar lines would be something like RP3, right? So that's take S3 and you divide out the C2 action that comes from the antipodal action, and say SO3, written by the special orthogonal matrices R3. So those are diffeomorphic. We sort of learned that in the topology 1 course, I suppose. And well, I don't know. I will let you figure out how to do this. Slightly similar flavor, but also interesting, is maybe CP3 and what is it? I think SO6 modulo U3. Okay. So I mean, this might arise if you're ever interested in finding out whether or not the sixth sphere has an almost complex structure and you're not willing to write one down. Then you could try to think about the space. So the space will tell you more or less the obstructions for an almost complex structure on the tangent bundle of S6. And because it's CP3, it's very easy to solve this. Okay, so these still are kind of not so different, right? All of these are essentially homogeneous spaces given by some V groups and modulo some subconvections. So maybe here you know what to do. Different example comes when we start not writing down manifolds which are homogeneous spaces, presented as portions of V groups, but where we start constructing things with manifolds. So a typical example would be, say, reconnect some of RP2 and compare that to a two-torus when you connect some RP2. And we call a connected sum means if you have two manifolds, you just remove a disk in each of them and then you glue them together along the common this one. You have to be a bit careful with orientations if they exist, but luckily RP2 is not orientable, so no worries. Okay, so these two are diffeomorphic, I claim, and I'm going to give you a hint of how one can prove this, and this hint is going to be sort of the prototypical type of construction one can do in manifolds that will be performed later. But also a different and related kind of thing would be you take CP2 and you connect from CP2 bar. So I said if things are orientable, you have to be a bit careful with orientation. So this is just taking CP2 and blowing up in one point algebraically. And so this relates to something I would like to write as S2 cross tilde S2. So this is the sphere bundle of the say non-trivial orientable rank 3 vector bundle over S2. Yeah, so if you are familiar with topology, you know how to do this, but if you're not, these things, so orientable rank 3 vector bundles on S2 are classified by pi 1 SO3, which if you solve the first exercise is easy to find out. Probably also not difficult to know from the definition of SO3. So there is two bundles, one is trivial, take the other one, gives you rank 3 vector bundle, take the sphere bundle. And okay, so I claim these manifolds are diffeomorphic, just as a small advertisement, or think if you like to think algebraically, manifolds have intersection forms, right? Manifolds satisfy congruity. These two being isomorphic says that this symmetric binomial form is over F2 isomorphic to this one. And this one says that this form over the integers is isomorphic. Okay, so in general, there's this principle of, from topology, you get algebra. If you have diffeomorphisms, you get isomorphisms of intersection forms. Conversely, it's not always true. From this observation, Friedman, for instance, tells us that those are homeomorphic, but we would like them to be diffeomorphic. So, yeah, okay. The exercise is to prove that all of these things are diffeomorphic, including their natural structure. Okay, so those are manifolds around. So let me give you a hint about how we can try to attack this surface. So, and okay, so imagine you have a closed surface. And now what I want to claim is that any smooth manifold, and it's a handle decomposition. Essentially that says that you can, I would say if it's connected, you start out with just with a ball, and then you start attaching handles to this ball. And then you start attaching further handles and so on and so on. For surfaces, this looks particularly easy. So what happens is that because, say, they're connected surface, then you will find such a handle decomposition with only one zero handle, and sort of by congruity only with one top handle. So you can remove that top disk, and what remains is just what you remove closed disk. What you will get is a picture of the manifold which has a ball, so a two ball, with a couple of handles attached. So anything will look as follows, I claim. So you will have your two ball, and then you will have to attach handles, and you will have to do it in a way such that the boundary of what you write down is still connected. So for instance, you're not allowed to draw this picture because then the boundary is disconnected. But you're allowed to, maybe I should do better. You're allowed to draw this picture. Okay, so if you circle through the boundary, it's connected, and claims this is the two torus. If you remove the top disk, and then this is the picture for the two torus. And then you can do this procedure, say, you can do it R many times. Okay? And then there's a different type of thing you can do because you have to, attaching these handles, you will have to glue in the endpoint of these intervals to the boundary. But I mean, you have to do this in a way that you have to specify the orientation. So either you can do them both in the same orientation, or you can twist the handle. So there are also these kind of handles around. Twisted handles. You can have those, say, as times. So this whole thing would be then a picture for the two torus. The R code to make it, some of the two torus to make it, some of the S code. And that's sort of the general way you can draw those surfaces pictorially like this. But now, of course, you observe that, well, I mean, you know, whether or not I write my handle like this or I move it over a bit, this is not going to make a difference, right? I mean, these two embeddings are isotopic, and some ambient isotopically blah blah saying that you can move this around a little bit, it will not change the diffeomorphism. But now, okay, let's have a little bit of fun and start moving this around, not at the boring places, but start moving this around over these other handles. Right? So what will happen if you start moving this guy over this handle is it will move inside here, but become twisted. Okay, so more or less the point is, the exercise you can solve from here, so you write down the correct pictures for these two handles, and then you perform handle slides. It's what translates to the other. So it's a lot of fun. Yeah, you can get quite confused, but I encourage you to do that. It's sort of a neat exercise. And right, in terms of algebra, again, I want to say that these twisted handles will tell you that your form is not even, in the sense that at some point on the diagonal you will find a 1. Whereas if there is no twisted handle in terms of algebra, you will always sort of have zeros on diagonals. Okay? So there's a close relation between how these pictures look at algebra. Okay, good. So with this you can solve this exercise. And I claim that sort of there is a similar sort of handle moves procedure or strategy for a simply connected form manifold, so for smooth form manifolds. Where that procedure is called curvature. So the diagrams become more complicated because the form manifold is more complicated than the surface. So encounter more stuff. But in principle, you can still write a diagrammatic picture of what a smooth form manifold looks like, and you can try to perform analogs in this thing, and you will, for instance, can do something like this. You don't have to do it like this, I suppose, but it's one way you can think about it. And the way, I mean, I want to present it like this because I want to convince you today that these, I mean, having these handles at your disposal and sort of moving them around in a geometric way will lead to an algebraic element at some point which is related to it. And it's really the way it's constructed, it comes from manipulating these handles in the geometry of the map. Okay. Right. So that's sort of all about closed manifolds. If you just have a closed manifold, you can start building it from scratch by having a zero handle like this disk and then attaching other things. And there's a relative of this function form, which says that if you have a coordinate, say going from M0 to M1, coordinate like this, then there exists a relative quantity. So telling you how to attach handles to M, from 0 to finally obtain either quantity. So you take one side and then you start attaching handles to that. So informally, I want to write this as well that your coordinate W looks like you start with M and for some reason you cross the interval on the cylinder. But that's most likely not the topology you're looking at unless W is also in the cylinder. So now you have to attach things to that. So what you then say is you attach some handle 1 or some dimension. You have a finite amount of handles that you add to build all of the coordinates. So just these are the handles. And then again, as in this case of a surface where there's only one handles, because then you've already done everything. Of course, here these have different dimensions. So the typical handle will be something like the n minus k, where this k is going to be equal to so in any case, there's some way of combinatorially, in some sense, constructing your coordinate from one side by attaching these handles. And then again, well, you can imagine if I just wiggle my attaching a bit, it will not change the coordinate. Right? So the point is that there's going to be handle moves that are allowed, which change your particular presentation as such, but will not change the diffeomorphism type of coordinates. And the point is that you can try to sort of do a from algebra to topology concept. There's a principle maybe. So algebra topology in a certain sense. So for instance, say we're in a simply connected case, say n equal to power w0, just for ease of verification, and assume that the relative homology of what do I write that? 0 w is 0. Okay, so that there's no relative homology. So for instance, you can say that maybe that's a better way to say that this is usually the homology. So such homology is going to go. So assuming you have a coordinate where the endpoint inclusion is a homology equivalence, there is no relative homology, and then there is going to be an argument in these handles like techniques that tell you you can arrange a relative handle decomposition with only k and k plus 1 handles for so you can pick some number which is suitably outside of 0 and the dimension of the coordinate, and then the statement is that you can find a handle decomposition where you only have handles into adjacent things. And now you can, okay, so that's sort of taking the information that some homology is not averages, and we manipulate these handles to get some. Now, from here, we can play the game back again and try to use this handle decomposition to calculate the relative. So, the relative handle chain complex will look like we have a couple of zeros. So the idea is that it will only consist of 3 modules, and according to how many k handles we have. So there will only be k and k plus 1 handles. So the chain complex will be something like, I guess, one and 2. Will only be in 2 adjacent degrees, but there is no homology. So that just means that the differential here is because there's no homology. And the main idea is that you incorporate incorporating pi1 correctly, so all these fundamental groups, well, then you will just work on the universal cover and keep the pi1 action into account all the time. So what you will find is that P is an invertible operator on the finite dimension, the finitely generated free so that's taking the pi1 action into account means that this is including 3 modules over the thing. And because it's an isomorphism, then there's going to be some invertible operator. And then the point is that this is going to determine a class inside the following thing. So you can just, this is going to be, okay, let's just say like this. So you can look at all invertible matrices over the time. Just make a union of all those for their genus unity pi. And that you can abelianize to the abelian group, and your element will give you your operator gives an element. Now, this element is not going to be quite well defined, mainly because of the choice of how you write this as a fused pi. Okay, so you have to divide something out. Maybe the subgroup which is generated by plus minus just the units by sitting inside here is just the 1 by 1 matrices. So these you have to divide out in order to get a relevant element, and it just turns out that this is the algebraic group of phi, the first one. So in the beginning I told you, algebraic K-tree is built out of modules and they're isomorphic. Using isomorphic is the element here. And then, okay, you have to divide something out, and this quotient is denoted as the y group. Okay, so from this description we obtain an element in this y-cat group, and now it's a sort of, okay, one can try to find out when is this element. Maybe I should also call this the torsion of W. So let's call the y-cat torsion of W, this element. And so this torsion is going to be 0 if and only if you can perform sort of elementary row and column operations to estimate the identity. Now, these elementary row and column operations can be sort of mimicked on a geometric level. So in other words, you can rearrange your handles slides to make your differential be reduced to having these one-on-ones everywhere. This will say that each handle has a corresponding k+1 handle, the one with where the entry is 1, that means. And these two are the only ones that intersect. All other ones are sort of destroyed from each other. And they intersect transversely at exactly 1 point. And then it's again a geometric argument, and those you can just cancel. And you can take both of them and delete them, and you will not change the path. So this group being 0 implies that W is isomorphic relative to M0 to be trivial. Because at the end of the day, removed all handles, you have to attach to V from M0 times I, W. And then it's just times I. So the main point is that this implies that M1 is diffeomorphic to M0. Because you can look at the other end of this diffeomorphism, run through this diffeomorphism, and you get a diffeomorphism. This might be a complicated diffeomorphism, and the fact that this might be complicated, or the fact is a complicated diffeomorphism, is the source for the Poincare conjecture performed topologically, and the two homotopy spheres are homomorphic to a standard sphere, but not diffeomorphic. Because somehow that, one creates a complicated diffeomorphism that you cannot in general sort of smoothly perform. Okay, so this whole construction is a theorem known as the Escobar theorem. Okay. So the Escobar theorem says that you can look at H coordinates over N, by which I mean a W and N and blah, blah, blah. Okay. And you divide out the relation of diffeomorphism of such relative to N. You look at diffeomorphism class of H coordinates over N, which are the identity of N. And to such things, by all these handle manipulations, we can associate a torsion in the y-cat group. And okay, the actual theorem, so what I explained is that if this element goes to 0, then I've tried to indicate why this coordinate is trivial and the same is in fact. So that's the H coordinate theorem, telling us about the set of isomorphism classes of H coordinates over N. So that's good. I mean, it's interesting, but in the spirit of the center and of many talks that were around, let's not only consider this set of isomorphism classes. So let's instead consider the moduli space of all H coordinates. So we're trying to upgrade to a better statement than only a bijection. Better version. A better version would be is to consider the moduli space H of M of H coordinates. Now we can think that a point in this moduli space will be just an H coordinate, and then where the path from one to the other is going to be a family of H coordinates over a simplex and so on. So you can build a sufficient space out of that. So there is a nice space of such H coordinates, and maybe we would rather like to understand the whole homotopy type of space and not only. So this is maybe the question that left-hand side. It's really made as the left-hand side. Okay. And I mean, this space is interesting for at least two reasons. On the one hand side, it's sort of the classifying space for bundles of H cobordisms. And it could well be that we have a manifold, all of which H cobordisms are trivial, but bundles might not be trivial. Right? So this is going to be captured by the homotopy pattern space. Without an interesting panel of H cobordisms space. But on the other hand, it also turns out that just as a side remark here, the group space of this space of H cobordisms is space of concordances. So those are essentially videomorphisms from n times I, n times I, fixing some point of the boundary. So most likely get confused with the videomorphisms that are the identity of the function. So it's sort of a flabby version of actual videomorphisms. And okay, so the space is also interesting. I'm just trying to understand what are diffeomorphisms or families of diffeomorphisms. So that's an interesting space. And this equivalence, this bijection, you can wonder whether or not this might be upgraded to a statement which tries to compute this space in terms of algebraic theory. Let's be bold and hope that something like this will be true, because this is something that is and the statement is that, as far as I know, this is not true or known or anything or expected, but so you can do the following stabilization. So there's going to be a map from the space of H cobordisms to M, and over M times theta 1. Just take an H cobordism and cross it before. Remain H cobordism. Sort of all these stabilization maps. This is supposed to have lost information about M because you didn't really care anymore about the particular M, you only cared about what remains after crossing within this. But it turns out the stable H cobordism space is in fact something you can describe that here. I should. So there is one important ingredient. This is a term of Musa saying that the map from H to M in stable H cobordism space is an iso on homotopy group for one line roughly lower dimensional. Can be better for particular n, but that's roughly what holds. And I mean, there's also a little epsilon down to the beginning. So I mean, if your manifold is too low dimensional, then it's for high dimensional manifolds, the statement is that the homotopy groups of this space, at least in the range, will be controlled. And okay, so this is also, this number is where this number also. Notice that 2n is roughly 2n. So this is something that's there, and then you can try to you can try to wonder whether or not the stable H cobordism space can be described in terms of algebraic theory, and there the answer is it's a term of so quite a stable parameterized cobordism term. Write all the unknowns. So with the history that I believe Hatcher announced the proof of it, which was not quite correct. Weizhausen reimagined how one should prove this, and then Weizhausen and Wolfmus finally actually finished a proper proof. And it says that there is an equivalence between this space of stable H cobordisms and construction purely intrinsic to stable homotopy theory and algebraic theory. So think that there is a map, and I'm going to try to explain some of the stuff. Okay, so I've already indicated that there is a gadget like this spherical group ring over loops M. It's some sort of ring in a generalized sense in homotopy theory, of which it still makes perfect sense to take K theory. And it turns out that, okay, so this is, I mean, in the technical sense, this is a spectrum or as an underlying space. And you have to take a manifold, view it as a spectrum, and then there's a canonical comparison map called the unit map or the assembly map or something. And then you can take the fiber of this map. And the statement is that there is an equivalent from this stable H-cobordism space to something that is purely described in terms of K theory. And now you observe the following diagrams. We have a space of H-cobordisms that sort of geometrically I think is interesting to do. And you can pass to the stabilizer. I want to stress that this loses information. This loses info, but only for I in a low range of degrees, it does not lose. Now here there is this equivalence to a fiber of such a K theory space, which it sounds very complicated, and in particular I haven't said anything of why any of that should relate to this K group of Z pi that we saw earlier. It's just some complicated homotopy theoretic gadget. But what you can do is you can use this the map by saying that there is a map from the spherical group ring just to this ordinary ring, which you I don't know. You can there is a world where you can view both on equal footing, and in this world there is a canonical map which induces something on K theory. So we also get something on this map from K theory. And now, well, this composite gives you a map from this space of H cobordisms to the fiber of the map from sigma plus M to the K theory of Z pi, just the ordinary K theory of Z pi. And it's an exercise to calculate that this pi 0. So that's the exercise we before. And now there's sort of one thing that we need to understand in order to say that whatever I've tried to tell you is a stable parameterized H cobordism term has anything to do with what we call it as cobordism establishing such a bijection. And the instance that goes into this is the following. So this is this key property of K theory I wanted to address. So key property of K theory is that, okay, so the name is this map. Okay, so what do we do this? This is what's technically called a ring spectrum. So it has a lot of higher homotopy groups potentially, and it has one zero homotopy group. And the claim is that this map is an isomorphism on pi 0, which just means, well, this space, I mean, it's a discrete thing. It only has one homotopy group, namely Z pi, sitting in degree 0. And this just is a canonical map from this ring spectrum to pi 0. So the statement is they have the same pi 0, but this term is much, much more complicated. And the key property of K theory is that after applying K theory, it's an isomorphism of pi 0 and pi 1. Okay, so technically speaking, for those of you who know about ring spectra or spectra in general, the statement is if you would replace this by an arbitrary map of connected ring spectra, which is an isomorphism on pi 0 and also an isomorphism on higher homotopy groups up to a given range, then K theory will add 1 to that range. It will be an isomorphism up including a bit more. Okay, so that's the property K theory has, which allows to calculate, of course, then you will find that this map is. Okay, so this is what comes out of this discussion. In other words, this equivalence between the stable H, this space of stable H cobordisms, and this K theoretic gadget is really sort of a lift to a space value version of this bijection that we found on the level of sets. And now the point is that one can use these kinds of ideas. leverage these ideas to compute and say in range things like rational homotopy groups of equimotic disks and rational homotopy groups of things like equimotic groups of say length spaces, or things that spherical space forms, and then I don't know, things that whose universal cover is a sphere, also rationally, and also maybe things like star homeomorphisms of n rationally if n has contracted with the universal cover, so-called the spherical manifolds. And the reason that these things work rationally but not integrally with what I proposed, or with these ideas that go into such constructions, has to do with the following fact. It has to do with the fact that the sphere spectrum, this guy, if you rationalize it, it becomes that. So that's a property of, I don't know, it's a statement that the stable homotopy groups of spheres are all finite, except in pi0 where it's zero. Okay, so that is something that you can leverage to say that this map, if this map were a rational equivalence, then there is an upgrade of this kind of version telling you that also the map on K-theory is a rational equivalence. So K-theory is sort of very sensitive to, if you have a map, which is a finite isomorphism, and it's an equivalence through the eyes of, I don't know, inverting P localizing, P addically or rationalizing or something, it remains so after applying K-theory. So you can leverage these kinds of arguments and hence get results about rational things from this point of view. Unfortunately, the sphere, if you want to localize the sphere at anything to become like Z, or something, a localization of Z, you actually have to dot all primes because it has torsion for all primes appearing. So this kind of gadget will not, this principle will not help you with anything better than rational calculations in principle. So this is the property of K-theory. But I want to tell you that there is different instances where you can make use of such invariant properties of K-theory that I'm going to explain now the rest of the talk. I want to say a couple of things that one can do to manipulate K-theory in the hope to obtain some calculations. And I think the applications of what I will present now are sort of orthogonal to the motivation, but nevertheless, this is one way that at least in these rational calculations, K-theory enters into the geometry of manifolds. Okay, so slightly different question is, how do we calculate K-theory? So if you have a particular ring in mind or a particular ring spectrum like sphere or something, I mean, how do you actually take it? And there are, of course, many things you can try to do. One prominent thing is so-called trace methods. Trace methods say something like there is a map from the K-theory of a ring to a gadget that really constructed. So these are kind of German characters. Or there's a cyclotomic trace. And it turns out from the theorem of Goodwillies and Dundas Goodwillie McCarthy that this gadget COR, whatever it is, it's sort of supposed to be more accessible to explicit calculations, but at the same time a very close approximation. So you can try to use such maps, calculate on the GC side, and deduce things about the K-theory side. And this was massively implemented by a lot of the hard work of Francis in that area. And there is many things nowadays known about these kind of trace maps, including there's a very beautiful result about the fire of the cyclotomic trace map, and also due to Dustin and Akil and Matthew about invariance with respect to the quotient of everything. So there's a lot of things one knows about the relation between K theory and, say, this homology, cyclic homology term. And if you're interested in inversion in the K theory, that's this easier or more classical invariant. Okay, so this is in principle saying that once you try to calculate something, you try to calculate this. The second thing you can try to do is just a general descent property. Well, not just read something like open covers, or maybe use image covers or something. There are many types of topologies on schemes or rings you could imagine, where you say maybe I can pick my ring apart into smaller pieces. I know everything on the smaller pieces. I put them together. So those would be descent properties of this kind. And one general thing you can ask in sort of commutative algebra or in algebraic geometry would be the question of the pi descent, which in general does not hold. If it does not satisfy this, it makes it more complicated to compute. But also by now there is a quite good understanding about sort of the failure of this pi descent. And again, Dustin very made great contributions in that area. There's a lot of things in this direction one knows by now. And a third property which is used for calculations is excision. So excision is more of a purely ring theoretic flavor, and it's more about, say, more about force color. So that is an example of what an excision property would be. And let me do an example which comes back to these two rings that we have. So at the end of the day, maybe calculate some explicit thing. So, for instance, you can do the following. If you let G be a finite group. For instance, you could imagine that G is the fundamental group of an n space. So on the manifold, take its pi1, suppose it's finite. And the typical situation of excision is as follows: is that you have a map of rings, and in this case, I want to take the map into something I might call the n, which is like QG, and this is the maximum form. So that is just the lattice inside QG containing the G end of maximum rank. So these things exist and are, from a ring theoretic point of view, much better behaved than CG. So I believe, for instance, if you take the cyclic here, then this maximum order will just be Z times the cyclic extension. So you add up the square root, like a P square root to Z. So better behaved than the And so the general question we have with excision is that you find an ideal inside CG, which is mapped isomorphically to an ideal, and then you divide out on both sides and look at a particular split. So the ideal you can consider is I being the one that's generated by the number of elements of G inside M. Right? And you get one that's generated by that. And then it turns out that this ideal, called the conductor ideal, is actually lies inside CG, not generated by the number of elements, but it is the lies. And so in particular, you will obtain the square of this pi. And okay, there's a general principle telling you this is a full deck square. And so one question is, if I K theory to the square is this a full vector? And okay, being a full vector essentially just means, so either you know what it means, then it's fine. Or if not, it just means that suppose you know 3 of the 4 corners, the K theories of 3 of the 4 corners, and then you will be more or less able to also calculate. In principle, it says that you can calculate the fourth term of the other. Okay, so that's a question you can ask, and the answer is going to be no. Unfortunately, K theory does not satisfy this. But what I want to tell you is that there is a formula for the K theory. Write down sort of how much it does not satisfy the decision. And So let me formulate a theorem which is now sort of a general situation, and then we can try to apply such methods to particular excision examples. Maybe I should also write down one other example that illustrates a bit better this idea of closed covers. Another example would be to take a ring K or R, and then you can look at something like how the non-varying its variables and divide out the product of R, and then okay, this is going to be a full deck of rings, and you think about this as the ring of functions on the union of whatever this is the ring of functions on, this is the ring of functions. So this sort of means this is an affine line, it's just the functions on the line. The other one is also the functions on the line, and so this is going to be the problem. Simple thing that you cover by these two coordinate axes. It's a closed cover, and you would like to know, can you calculate the k-theory of this curve in terms of all the three terms? And again, the answer is no, you cannot, but you can try to understand what is the k-theory. When you give a formula for the k-theory. And okay, so the general term one can prove in this direction. Is the following. So we can just generalize the situation a bit and first consider an arbitrary square, so a full square of rings like that. But you are absolutely free to think that all rings are just ordinary rings. And then it would be good. So in all of these situations, from here to observe that some logical map is surjective. So probably best to think if you think in the discrete case, just think of a case where you have a surjection like this. And this will be exactly the case if you have a map from A to A prime, which sends an isomorphic the other idea, and then you just take the portion. So that's sort of the general situation you do that. And then the claim is that, well, then there exists a new ring, which is they get some formula, and I'm going to abbreviate it like with circle dot. So it's denoted like this, but let me just write a little circle dot for it. And the diagram, which is of the following shape. You still have your good old big diagram remaining, but then you insert this little circle dot inside. Okay, so this is now the hash code say. And the statement is such that this hashtag diagram is. So in other words, this really just means that this implies that if you wanted to know whether or not K-theory applied to the original diagram, this is or whether or not you can calculate and say the K-theory of this guy in terms of that diagram, this one. Well, our theorem tells you you can calculate it in terms of this, and this one. Well, so in other words, it happens that this guy is equivalent if you only have circular to the pilot. Okay, I mean, this is maybe for the moment it sounds a bit, how useful is it? And I think it's very useful because it tells you that the question of whether or not this diagram is a full vector, sort of it has an answer, so to say, before a line. So for instance, if you can show that this map is an equivalence of rings, then obviously K-theory will be an equivalence. And you don't have to prove anything complicated about K-theory. You put something before applying it, and then it will be defined. And this kind of idea that you have a formula for the failure of excision before applying K-theory can be leveraged to reprove a couple of things that had been known previously and sort of just, from my point of view, capture or like organizes a couple of the arguments in this manner. So some consequences. Oh, yes.
Yeah, reversal properties.
No. It's a construction. And the construction is also, yeah, no. So in general, it is hopeless to think that this ring will be uniquely determined, I think, or maybe. But no, it's not given in terms of universal property on the level of rings. In fact, the way one proves this is to pass everywhere to categories of modules. To prove a statement about, so that you find the category of modules that sits here, and then you prove that it comes from, it is the module category of a ring. But I'm not aware of an a priori universal property. But at the very end, if I'm allowed, in some situations, it does have a particular universal property. I can tell you afterwards. But in general, this is quite mysterious. But what I want to say is that although it's quite mysterious, it has some formal properties that don't allow you to exactly say what actually this ring is, but which suffice to prove the following consequences. So for instance, if you can, so suppose this ring, this is all this ring is like in this example, these kinds of squares, they are called Milnor squares. So if you're in this situation and you happen to know that the form for A prime and B over A, right? A prime and B are modules over A. You happen to know that this would stand for say the range 1 less or equal I less or equals to n, then you will prove that this map is which has to do with the fact that we can just calculate the homotopy groups of this ring. They are just given by these small groups abstractly. So if they vanish, it tells us that the map from here to here is an isomorphism or many homotopy groups because of all of them. Then these kind of things you can use. And the consequence that you obtain is that you sort of have a long exact sequence of Manifolds type in K-theory relating this, and this in a range. Right? Because in general, you have it if you include the circular ring, but in this little range, you have an isomorphism to this one. And so this consequence was the fact that this is decision theorem. So this can get a very intricate argument using group homology arguments to prove something about what kind of squares will give rise, at least in the range, to these bilaterals. And you can sort of reprove it by the mere existence of the circular ring plus this property that you can describe the homotopy like this to obtain a result along these numbers. And there are many variants that we now use, all of which build on the fact that we can control the quality of this map through the eyes of K. Always by saying it induces an isomorphism in terms of homotopy groups, or it induces an isomorphism rationally, or after P completion, or these kind of things. And all these properties persist after the map. So these are the general methods that you can use to apply. So for instance, you could try to apply such a result to that square, and it will tell you at least that this square is going to be rational. So if you're only interested in calculating rational K-theory CG, then it will turn out you might as well calculate the rational K-theory of n, which is a firm of Borel's that's also sort of well known. But nevertheless, you can try to play these kind of games on the K-theory side. So I will finish with saying that, okay, so currently a lot of my work, partially, of course, revolves around understanding the circular. It's a bit intricate in general, but I hope that we can sort of give formulas for it in particular instances and actually also use it at some point, coming back to step one, using trade methods to actually calculate things about k-loops in particular examples once we actually give this formula. In some cases we have. So that's one of the portions I think about, but I deliberately wanted to tell you about, the relation of manifolds, of which this is a bit unrelated, to also, let you know that I also like geometry, manifolds, and things related to coordinates and categories, things Oscar is going to explain about. So if you're ever interested in chatting or just doing that along these lines, then I'd be happy to do so. And so thanks for your attention.
You know what the circular is if this is calculated, like G is sigma about P, isn't it?
Yes, I think so. So I think, but okay, so it's a formula and then you're still going to say it. But I think if, say, let me do this guy, then I'm not going to work with this square, I'm going to take a different square, and I think you can, if I understand correctly, you can go to the sigmotomic extension, and you can go to Z, and then this is going to be full data over. And I believe that, so this comes back to Fabian's question, so there's a general principle. So of course the polynomial ring maps to it. And also maps here. Yeah, you can observe that Fp is the tensor product over this guy, and that. That is going to be. I mean, unless I thought about this morning, I hope this is correct. But unless, so I think this is true. So it will turn out that you can write this lower term in terms of a relative tensor product of the outer terms along something which sits beneath the guidance model. Whenever you're in such a situation, then the conclusion is going to be, so that's something that I'm currently trying to write up with Leo, is that the circular ring is going to be a push out of E1 ring spectrum. And then it's going to be where this is. So the Z push out of E over T. The and I need to write this as okay, and then sort of in a homotopy theoretic sense, you set T, so the general some P through the theory T1. Right. Almost a P. I think that's sort of the form that you get out in this. In general, these rings, these circular rings in situations of that kind will be sort of really type of push up. So for instance, in the case of the circular, this case, the circular ring we just polynomial ring is a variable to be 2. So yeah, typically in a lot of examples we'll find such three kinds of algebras of 3 dividing out certain relations in the E1 world. And of course, I'm calculating the K theory of this, I guess, is don't have a clue. But of such things is I suppose, much more tricky. So that's one of the things that we have to work out in the future. Yeah. But okay, yes. Yes.
So you mentioned P is not dividing the cost for the ring at the beginning, the number of your application.
Yes.
Your studies. It's a hard statement. So what happens now? Can you characterize the property that P square is not dividing the cost?
I have yes, I have no clue. Dustin, Jim, I have no clue. I don't know.
Very clear. I'm not noticing some expression now. But then you have to look very closely to see what it is. I mean, everything you can express in terms of your solid theory, you can also read off here in some way or another. But you have to look to see what it is. It wouldn't be as simple as something like that. You might even need to look at other system extensions in their case in principle.
So you said this circular thingy is defined in terms of a category first. So what is that?
The category?
Yeah.
Yes, that's actually quite easy. So what you do is from this original diagram, you can look at something like just the perfectly right category. Yes, homology theory of chain complexes up to quasi-isomorphism. Fine. And now, okay, so the statement is going to be that you can like this. So what you can construct is a category that we write as P. So that's a category which consists of an object in the derived category of A prime, an object in the derived category of B, and a map from the base change of X over A prime with B prime to Y. Not an isomorphism, but just a map. And okay, so this you can look at. And it turns out that, okay, this kind of you can think about as like sort of like a bundle of BP categories over BPA. Right? It's not a product, but it kind of. Yeah. So okay, this is not a product category because there's this morphism there, but through the eyes of K theory, it looks like a product. You can forget the morphism. So K theory of that category is just the product of this one there. And now what you show the fact that the diagram that we started out with is a full vector, is that there's a full vector distribution of categories like this. You can just pass through the quotient of categories. So that's something that now that we have this language of higher category theory around makes sense. It's just on Verdier quotient, not on the level of triangulated, but on the level of stable infinity categories. And then you see that this category is generated by A prime, this one is generated by B. So in this category, you have two generators, one coming from here, the one coming from there. But in this quotient, you've identified both. So this category is going to be generated by a single object, and then it's a content of this theorem of Schreiner and Shipley that single object, its endomorphisms have the module category precisely Q. So this is going to be the category of modules of the right category by the Schreiner-Shipley theorem. And then I mean, that's all sort of trivial. The only thing that we then have to work out, which is also not very complicated, is to calculate the homotopy groups of this string and to calculate sort of at least the underlying maps of spectra that are around. You don't have to describe what, I mean, just the formalism gives you that this is a diagram of rings, and the map of rings, you know, is as, it uses an isomorphism on homotopy groups if and only if you forget that it was a map of rings, and it does. So in order to calculate the quality of this map in terms of the homotopy groups, you don't have to know about the ring structure and everything underlying. You can just calculate fully from this description. So it's very easy.
Any more questions? Markus? Okay, if not, thank you, Markus.